Welcome back. We are now in section 4 of chapter 4. This section is called Families of Functions and Modeling. Way back in chapter 1, your book talked about families of functions, though that was in sections 1 through 6, somewhere in there, so we didn't talk about it in class. But it's back there if you want to go review families of functions. But the basic idea is this. A graph of one function can tell us about the graphs of many others. For example, the graph of y equals x squared indirectly tells us about the graphs of y equals x squared plus 2, y equals x plus 2 squared, y equals 2x squared, and many others. We say that all functions of the form y equals so all functions of the form y equals a times x plus b squared plus c form a family of functions. The values a, b, and c are called parameters and sorry about that. So the values a, b, and c are called parameters, and different values of the parameters give different members of the family. One reason that we like studying families of functions is their use in mathematical modeling, because a crucial first step in mathematical modeling involves recognizing families of functions that might fit the original data. So we're going to look at a couple of different families of functions. First up is the family for motion under gravity. In this case, the family of functions look like this: y equal negative 4.9 t squared plus v naught times t plus y naught, where t equals time in seconds, v naught equals initial velocity, in meters per second, and y naught equals initial position, in meters. And then what about y? Well, y is giving you the current position in meters at time t. Next up, we have the bell-shaped curve family. So functions in this family have this form. Y is equal to e to the negative x minus a squared divided by b. So this is used a lot in statistics. We are not going to get into the details here, but if you want to learn more about it and want to use it, take stats with me in the spring next year. Next up, exponential models with a limit. So in this case, we've got y equal to a times 1 minus e to the negative b x. Something similar, I'll leave it there so you can see both. Something similar is the logistic model. Logistic model, we've got y equal to L divided by 1 plus a e to the negative kt. And this logistic model models population growth in a limited environment. So those are the couple of types that we're going to consider. This was just a very brief look at them. If you want to know more details of them, your book goes into some of the more theoretical details. If you want to go read that, we're going to do 2 examples to show how you could use these. So in our first example, we want to give a function describing the position of a projectile launched upward from ground level with an initial velocity of 50 meters per second. And how high does the projectile rise? So first off, we can read this and see what we know. So we've got ground level, we've got 50 meters per second, projectile launched upward, we're interested in the position. So what we know here is our initial starting position was on the ground, so y naught is 0. Our initial velocity was 50 meters per second. That is enough for us to write our function. Our function, based on the format we saw before, is negative 4.9 t squared plus 50t. So that gives us the function. And now we want to know how high does the projectile rise. So we want to find a maximum. And what can be helpful here is to think about what this looks like. It's going to look like a parabola, right? So you're going to, the projectile is launched up, it goes up, 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 but eventually it does come down. So you've got like a parabola thing going on here. So we know that the max is going to be right about there. To find the max, take the derivative, set it equal to 0, and solve. So the derivative is negative 9.8t plus 50. So take that, set it equal to 0, solve for t. We get 9.8t is equal to 50, so t is equal to about 5.1. Okay, so that's when the max occurs, but what is it? Well, let me erase my picture. At 5.1 seconds, y is equal to negative 4.9 times 5.1 squared plus 50 times 5.1, which is equal to 127.551. So a maximum height of 127.551 meters is achieved after 5.1, or I guess at 5.1 seconds. We'll go ahead and do another example. The number of people n who have seen a viral tweet on Twitter by time t is modeled by n of t is equal to a times 1 minus e to the negative bt. So that's our exponential model. Suppose there are 200,000 people on Twitter who will see the tweet eventually. If 10% of them see the tweet in the first day, find A and B. And assume that time is being measured in days here. Well, a fact about this type of model is that we know that the limit as t approaches infinity of n of t is a. So we know that about this model. So that tells us a is equal to 200,000. So where do we get that? Well, the book tells us, this first statement here, that the limit as t approaches infinity of n is a. And kind of in words is that's, after forever, eventually, what's n going to be? Well, it's going to be a. Well, we said eventually 200,000 people will see the tweet, so a is 200,000. We also said that 10% of them see it on the first day. So that tells us when t is equal to 1, n is equal to 0.1 times 200,000, which is equal to 20,000. So 20,000 people see it on the first day. So let's substitute that into our equation and see what we get. N, evaluated at 1, is 20,000. That's equal to 200,000 times 1 minus e to the negative b times 1. So we want to solve for b. We've already found a. Solving for b, start off, divide each side by 20,000. Well, actually, I'll go ahead and rewrite it so we see what exactly is going on here. So we've got 20,000 is equal to 200,000 times 1 minus e to the negative b. So that tells us 0.1 is equal to 1 minus e to the negative b. E to the negative b is equal to 0.9. And then b is equal to negative ln of 0.9, which is about 0.105. Let me just double check one thing. Okay, good. Wanted to make sure I didn't mess up any negative signs or anything here. So that gives us A and B. So A is 200,000. We said that up here. A is 200,000 and B is about 0.105. That's the end of section 4.4. We're actually going to skip section 4.5 and go to section 4.6, but we've already done 4.6. So we'll actually be moving into 4.7 next.